Our second speaker this afternoon is Carl-Fredrik Nyberg-Brodda from the Korea Institute for Relevant Study, who will talk about the growth of free-inverse semigroups.
Well, thank you. And thank you to the organizers for inviting me and giving me a chance to speak here. Now, I'm one of those people who was not yet born when the first version of this happened, in the sense that I was doing my master's project on Burger Moses groups, which was very nice because I had the pleasure of meeting Mark Berger for the first time at this conference. I felt like coming full circle. But in fact, I won't at all be talking about Burger Moses groups for this talk. In fact, I'll not really talk about groups at all in some sense. Now that I have you here for an hour, you're not allowed to, in polite society, you're not allowed to leave. And so I have an hour to corrupt you. Because you'll see this is joint work I did while I was my first postdoc in Manchester, which was in semigroup theory. And the first two people, Mark Cambites and Nora Sarkach, they're semigroup theorists. Cambites, you might have seen the name in some rag stuff, but he's a semigroup theorist, fully now. But the third name is Richard Webb, who you might not know as a semigroup theorist. But over the year that I was there, the three of us, with joint effort and lots of nice theorems, were able to persuade him and corrupt him. So we had a full year and three of us to corrupt one person into doing semigroup theory. I have 58 minutes, and there's one of me, and there's a room of you. But I like a challenge. That's mathematical challenges, right? So I think I'll get started right away. Now, I won't assume any prerequisite about inverse semigroups or anything like that. But I will start with a little bit of semigroup theory, just to get us going. And just for a quick reminder, so a semigroup and monoid, at least for me, will be basically the same thing. It's groups without inverses. Now, with a monoid, you also have an identity element. For me, I'll be very, very lax about this requirement. I'll typically assume there's an identity element, but the important thing is it's associative, and that's it. Identity you can add if you want. And there's a natural thing you can do, which comes from ring theory. There's something called von Neumann regularity in ring theory, which you might have seen. It's a very nice condition, especially homologically speaking, which is saying that for every element in my monoid, there is some y such that I can kind of weakly invert it, this first x. So xyx is x. Well, if I take y to be x inverse, of course this is true. Right? So it's a kind of weak inverse, which is usually called a pseudo-inverse. And an inverse monoid is one where this is unique. I mean, it's really, this is as, spot the difference, and there's an exclamation mark, and that's the only difference. But it turns out that these are quite different objects in general, and there's a very nice theorem that was proved here in Cambridge by famous semigroup theorist Roger Penrose and Douglas Munn when they were grad students together at St. John's, and they sat down over lunch at one point and proved that a regular monoid is inverse if and only if the idempotents commute. Now, what are the idempotents? Well, typically there can be lots of them, but usually if I have something like, in the regular setting, if I take xy, and I have that x and y satisfy these equations, well, what happens when I do xy times xy? Well, xyx, it's associative, that's the only thing I assume. xyx is x, so this is just xy. So that's an idempotent. And if all of these commute, then it's an inverse semigroup, an inverse monoid. And the converse is also true. And it's a nice little exercise in crunching out some algebraic equations. And it's a very nice example of non-trivial algebraic reasoning, really like churning out the lines and lines and lines of algebraic manipulations to get something that's quite nice. And it's also Roger Penrose, so it's always nice to, it's really the same guy. He went on to do some other stuff afterwards. So there's something in what's called universal algebra, which is when you're moving away from groups and semigroups and into sort of algebraic structures that have some signature and all sorts of really quite nasty things that I won't get into too much. But there's something called the HSP theorem, which roughly says, which was Birkhoff proved in the 30s, which says that if you have something which is closed undertaking homomorphisms, closed undertaking subobjects, and closed undertaking products, so H, S, and P, homomorphism, sub, and products, then you have what's called an algebraic variety, and there exist free objects. There's something satisfying this universal property and category theory. But this is a purely uniqueness statement, and I won't be using this HSP theorem at all. So you can ask, well, what does something that's free in this inverse world look like? Because, well, you might know free monoids or free semigroups. That's just another word for saying it's the set of all words of an alphabet. And free groups, well, we certainly all know free groups. It's taking the freely reduced words. We have a kind of word model for it. We can model these structures purely based on alphabets. So what do free inverse monoids look like? Well, there's this old proposition by Wagner, not the one who became a bit more famous recently, but rather just this is 70 years ago, where he basically says, well, instead of here, the point is that in free groups, we have to quotient out, we have to identify some things. We have to identify x inverse with 1, and x inverse x with 1. And this is basically saying, well, we have to identify all of these relations that we should have. This xyx is x and yxy is y. We need to identify that, and we also need to make sure that these idempotent-like things commute. And once we get that, we get a free object. Now, if you stare at this, I mean, free groups, I know how they work. We all know how they work. But I have zero intuition just staring at this, what kind of words will be identified. I know some of them which will be identified, but which ones will be? So in other words, can I solve the word problem? If you give me 2 words, can you tell me whether they get identified under this sort of equivalence relation or not? And there's 2 natural questions you get here. The first one is, what do free inverse monoids look like? And the second one is, why are there semigroups in my conference on non-positive curvature? Because what does this have to do with non-positive curvature, right? What's the connection? And it turns out that there's actually a very, very beautiful connection with a lot of geometric group theory, which is going to be underlying a lot of the stuff I do. So if you bear with me for a second, I'll go through a very, very beautiful construction for solving the word problem. Because this was really an open problem for a while in free inverse monoids. We didn't really know. This was a hot topic in the 70s. And it turns out that one can use a beautiful combinatorial construction called Munn trees. This is the same Douglas Munn. And so a Munn tree is a very, very simple idea. You take you want to construct a free inverse monoid on a set. You take the free group on that set, and you look at the finite connected subgraphs of the Cayley graph. So you just draw out some path, and you take that, you distinguish one vertex, and that's it. That's a Munn tree. That's the definition of a Munn tree. And yeah, you just read out some words. So I mean, this first definition is really kind of defining what a Cayley graph is in some way, in a different language. And just to give a very nice example, well, to find the Munn tree for any word, you just read W in the Cayley graph, you record which edges and vertices you go to, and then you mark your endpoint, and that's it. So just for a fun little example, for the Munn tree for this word, which is, I mean, you can see there's a lot of free reductions you can do here, but you're not allowed to freely reduce it, because we're not in a group. This is not, we don't have that XX inverse is 1, but we do have that there's these sort of pseudo relations. And so you just read this, a squared, a to the minus 3, a, b inverse, a, b inverse, b, c. I wish I could draw in 3 dimensions in this, but there you go. C, a inverse, c inverse, and then you mark this little beta endpoint with a different colored vertex, and that's a Munn tree. Super simple stuff, right? And it turns out that in this horrible congruence thing I wrote up before, this can be completely characterized in terms of these Munn trees. So 2 words are equal in the free inverse monoid if and only if they have exactly the same Munn tree, including the end vertex. So do they trace out the same path in the Cayley graph? Yes, then they're equal, otherwise no. And so in particular, we can certainly solve the word problem. We can all draw the Cayley graph of the free group. That's very easy. And so one might wonder, well, so suddenly we have this geometric object, the Cayley graph of the free group, and it's somehow reflected in this combinatorial object that I've introduced to you, and maybe you've seen it before, but these weird free inverse monoids. And actually, the connection goes a lot further, and one can consider arbitrary inverse monoid presentations. So I'll write them with this inv, just to distinguish from GP, group presentations. Yeah?
So do you record the order in which you run over the edges, or just the tree?
No, just the tree.
Just the tree.
Just the tree as a graph. No order, nothing, yeah. Because the point is that this is what's capturing the idea of like a local inverse. So no matter how many times you go across an edge, or whether you do it again, you're just kind of erasing it. And, well, if I have something like, let's say I have this graph, and I read A here and B here, well, basically I'm saying that the order that let's say I start here and I end here, I'm saying that the order I traverse this doesn't matter. Well, what does that mean? Well, it's saying that A inverse, B inverse, should be the same thing as B inverse, A inverse. And that's exactly saying that idempotence commute. Right? And that's one of the conditions. So there's a very, very, very geometric interpretation of these idempotence commuting. Namely, it doesn't matter which order you go in. If you have a path going away, doesn't matter if you do that and it comes back. Doesn't matter if you do that before or after. But good question. And so we can consider inverse monoid presentation. So we add some relations. We make some more words equal. It's a perfectly sensible thing to do. And of course, since we have these distinguished inverses, we can just force XX inverse to be 1 if we want to, for all these letters. And we get a surjection, obviously, onto a group. We surject onto the group with the same presentation. We can always do that, right? If I take this free inverse monoid and I force XX inverse to be 1, well, I just get the free group. It's just, I'm really just saying that elements will be, these connected subgraphs will be literal elements of the free group. And this is called the maximal group image. And there's a kind of technical condition where something called being E-unitary, which means that the only things mapping to the identity element should be the idempotent. So the things that are that square to 1. Because of course in a group, there's a fantastic line from the beginning of a book on semigroup theory, which says that in spite of only having one idempotent, groups tend to be interesting to study. And this is a very good line, and of course there's only one idempotent in groups, and any idempotent under a homomorphism has to map to an idempotent, and so we'll certainly collapse everything into 1, but there might be other things mapping onto it, and that would be bad. Unitary is a niceness condition, and in that case it turns out that there's a lot of geometric information that one can deduce about the monoid itself purely from the geometry of the group. And here's an example of the kind of statements. I won't get too much into this because I'll mostly be talking about the free objects, but just as an example of how these geometric statements work. And it's basically saying that if you have an inverse monoid, then this will be E-unitary if and only if there's something called the Schützenberger graphs for every word embed naturally into the Cayley graph of the maximal group image. Now, I haven't defined what the Schützenberger graph is, and loosely speaking, what it is that when you take, that's a very expected effect of what I was about to do. I should have thought of that. I'll draw here instead. So you can, whenever you have any algebraic object, you can always look at its Cayley graph, just like in groups, and you multiply on the right to get your edges. And let's say you start at 1, you might be walking around in your Cayley graph somehow, and you might be able to return. There's some elements going back and forth. And you can identify what the strongly connected components, so the bits where, just by multiplying on the right, you can always return to where you started. You can always do little loops. And groups, of course, you can always go back to wherever you want. You have inverses. But in this land, you might not be able to do that, right? You might not be able to invert what you've done. And the Cayley graph typically decomposes. It always decomposes into these little strongly connected components. And these are called Schützenberger graphs. That's very, very loosely, without going too much into detail what they are. And the nice thing is to construct these, all one needs to do is do Stallings foldings and apply the relations of the presentations. And so one can construct these purely from a group theoretic point of view. And this E-unitarity condition essentially says that there's nothing else that happens. You really just have the geometry of the groups being reflected in this inverse monoid structure. And there's something called group age classes, which is this funny age. If you could identify that's an age. I'm always terrible with these /math SCR letters, but that's an age. And looking at the automorphism groups of these strongly connected components reveals algebraic information about the monoid. Now, automorphism groups of graphs, or Cayley graphs, well, as long as they're connected to groups, suddenly that's geometric information. And don't worry too much about this thing. I really won't be going into this too much. And there's a nice recent theorem by Bob Gray, Pedro Silva, and Nora Sokach, which says that if you have that all of these these strongly connected components are quasi-isometric to trees, then you can solve the word problem. This is roughly speaking saying that we have a virtually free inverse monoid, whatever that should be. But on the other hand, if we only require these graphs to be delta hyperbolic for whatever delta, even if it's uniform, then the word problem can be undecidable. And so suddenly there's something more going on. There's both the geometry coming from this group theoretic side, but there's also some strange thing going on in general. And there's all sorts of, well, lots of, I mean, it's a whole subject that I really can't get into too much, but called geometric inverse semigroup theory, which is really exploding at the moment. There's several articles every year by usually kind of a closely knit group of people, where there's theorems of this form and trying to extract geometric information purely based on maximal group images and talking about group distortion and all sorts of really nice stuff. So I'm sure that in the future there will be lots of really nice applications of, well, essentially studying non-positive curvature in the context of these calligraphs. Now I can't get too much into that, but I can, but hopefully this convinces you that there's something geometric underlying these objects, and these inverse monoids are not arbitrary, strange algebraic constructions. Okay, so let's return a little bit to these free inverse monoids, or free inverse semigroups, and also to the title of my talk, which is the growth of free inverse semigroups. Now, we all kind of know what growth is. Certainly in the context of groups, it should be familiar, but it also applies equally well in the context of whatever algebraic structure you want, and including in semigroup theory. So I'll just do a very quick recap of this. You can always, if you want to solve the word problem in some finitely presented whatever, you can always compute the balls of radius something. You can try and make things equal. It's kind of, and if you have a nice bound on the din function, like we saw in a very nice earlier talk, you can understand when these well, whether you're done constructing these balls or not. And it turns out that kind of computing how fast the balls in a calligraph grow, you can compute that if and only if you can solve the word problem. This is not so hard to see at all. And this is true for groups, and it's equally true for any algebraic structure. And the growth function is just, well, the function that maps any number to the size of the ball of radius that. And it's with respect to a finite generating set. I'll be a little bit lax about that in general. Typically, I'll be fixing what the finite generating set is. And of course, let's say we have exponential growth. We can just define what that growth rate should be. So if it's 2 to the n, the growth rate should be 2. Right? And that's just what we're saying here. If we have something that has growth rate more than 1, it's exponential. If it's polynomial, it's polynomial. And otherwise, like the miscellaneous category is the intermediate growth, right? And I'm sure you've all heard of groups of intermediate growth, and I'll give some very nice examples here. 3 very, very basic ones is, well, free monoids, they grow like 2 to the n, or k to the n if you have k generators. It's like just an infinite binary tree in this case. Free groups, well, we all know how free groups grow. They grow like, well, in rank 2, we just subtract 1. We times 2 minus 1. Just for an example of something that's, also exactly the same as in the group case, if we take the natural numbers across the natural numbers, well, that's just an infinite grid. It's one quadrant of an infinite grid. Of course, that grows quadratically, right? Suddenly, there's a slightly interesting example, something called the bicyclic monoid, which looks something like this. So, magically, that appears. Excellent preparation. So it looks something like this. We have this relation b times c should be equal to 1. And if you're in group land, you'll just say, well, that's z. But in this is not group land. And the point is that even though b times c is 1, we don't have that c times b is 1. In fact, c times b is not equal to 1. Because, well, if I have that b times c is 1, well, whenever I insert or delete a bc, well, any word equal to 1 that's non-trivial has to start with b. And c doesn't start with b, and so cb is not equal to 1. And so the calligraph looks something like, well, I can read b, and of course I can always invert that and go by c. Similarly, I can read lots of b's, and then come back. But as soon as I read a c, I've kind of fallen out of this category. And now I'm kind of stuck here. And unlike in the world of groups, I can never return. So once I've read the c, I have some non-trivial ideal going on, and I have to be stuck here. And actually, if you stare at the picture I drew over there, this is a particularly simple example of an inverse semigroup. So B is C inverse. and C is B inverse. And these are these strongly connected components, right? No matter where I am in here, I can always go from one vertex to another by a set of edges, but as soon as I fall out of them, I can never return. And looking at the geometry of these, which are very simple, they just look like n, right? Like the natural numbers, understanding the geometry of that gives you information about the entire thing. Now, this is a very pathologically simple example, but it's already somewhat interesting from that point of view. And of course, what's the growth? Well, I have 1 here. The ball of radius 0 is 1 element. The ball of radius 1 is 2 elements. Ball of radius 1 is 3 elements. And then I have 3, 4, 5, 6 elements, and so on. And it grows like sort of these triangular numbers. Okay, quite simple. Of course, we know that if we have a nilpotent group that's degree D, a D-step nilpotent group, then we can, it has degree D polynomial growth. And also the converse is sort of true. If we have a finite generated group with polynomial growth, it's virtually nilpotent, if and only if. And you might wonder whether there's something similar for semigroups. Can we characterize some sort of nilpotency? But already we get into problems of how do we define nilpotency. And there's a nice intermediate thing here with Grigorchuk, who proved that, as you probably know, there are finitely generated groups with intermediate growth. But you might not know that Grigorchuk is a semigroup theorist. And he proved that if you have a finitely generated cancellative semigroup, which is a kind of intermediate, it means that you can cancel on the left and cancel on the right, just like in groups, then they satisfy, if it has polynomial growth, then it turns out that they satisfy some non-trivial identity. So if you, two sides of an equation, you plug over, let's say, x and y, and if you plug it, no matter what x and y you plug in, it will always be satisfied. So this is certainly true in nilpotent groups. You know, the d-step iterated commutator, no matter what you plug into that, it's going to be 1. Right? And actually, it turns out that that's true for semigroups too. And there's this horrible example from 1993 by Okninsky, which is really beautiful. And this is something like, if you take away nothing else other than this, it's that semigroups of matrices are really interesting. So you take these two matrices, which look very, 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 very innocent. Then the ball of radius n in the semigroup generated by those two matrices grows like, has intermediate growth. This is very strange because when you think about groups of matrices, you might think of, its alternative and other similar very nice examples, but semigroups, things break down. And there's lots of interesting combinatorics going on. Okay, so hopefully that's enough to kind of make it clear that even the polynomial growth world or intermediate growth world, there's somehow lots of unexpected things that can happen, and that's why that will be one of the key themes of the remainder of the talk. Okay, so
if a semigroup has intermediate growth, does it mean any subgroup of it, any finite generated subgroup of it also have intermediate growth?
Well, I mean, you always have the trivial subgroup in there.
Well, okay.
But maybe it's locally and for the nice. So sometimes you won't even find any, probably if you look at inside this thing, there are probably no non-trivial subgroups. Unless I'm being, well, you have some sort of, I don't think there are any non-trivial subgroups hiding in there. So really, sadly, one is lost in if one tries to understand these in terms of groups, very often one becomes lost immediately. Or, one is blessed, right? One is free from the shackles of group theory and has to start thinking about difficult things like semigroup theory. Yes?
So is it, when you discuss growth of semigroups, is it possible always to present it like positive words in some group?
No, I don't think so. So even these cancellative semigroups, so by that I just mean you can cancel on the left and cancel on the right, even they will typically not be embeddable into groups. And when they're not group embeddable, I mean, it's a very reasonable question, but I would suspect that the answer is no. And in general, these things will be very horrible. Right. So, well, then we can get. I've now introduced free inverse monoids. I've introduced growth. Well, you knew what growth was, but I've convinced you that it's a reasonable thing for semigroups. So we can get to the title of the talk: growth of free inverse monoids, or semigroups. And well, let's go back to thinking about what were these free inverse monoids. Well, it was these collections of Munn trees. So finite connected subgraphs of the free group with distinguished vertices. And it's not so hard that if you look at the free inverse monoid of rank 1, now if you're a group theorist, well, rank 1, that's like Z, right? But this is a little bit more tricky, and we actually have cubic growth. So what's that like? Well, what's a Mun tree in the case of rank 1? Well, it's a finite connected subgraph of Z, right? With one distinguished endpoint. So it would look something like this. We have our identity element here, and let's say our generators are called X, or the generator is just called X. We get some graph that just goes something like this, and then we have some distinguished endpoint. And this is a 3-parameter kind of thing, right? We have some leftmost thing we get to, we have some rightmost thing we get to, and then we have some distinguished endpoint beta. And this alpha, beta, gamma, they're sort of independent of each other. N times n times n is n cubed. That's the kind of rough explanation. It's an easy thing to prove, right? That's how many finite birooted subpaths there are of Z. That's another way of saying it. So there was a natural question that we sat down to think about, and we also roped in Richard Webb into this question and managed to convince him that it was fun, which is what's the exponential growth rate of higher rank free inverse monoids? And I say exponential because, well, certainly, well, the free group is going to grow slower than the free inverse monoid of the same rank. And why? Well, because we've added more relations, right? I mean, if I quotient out by XX inverse for all my x's, well, then I'm just going to get the free group. So certainly, by adding more relations, I go to the left, and that means slower growth. More relations means the growth has to be slower, right? But on the other hand, if I don't add any relations at all, I just have all the words over x and x inverse, well, then I have the free monoid of twice the rank. So the growth has to be somewhere sandwiched in between here, and we know that, well, the free group grows like 2r minus 1, and the free monoid grows like 2r. So the exponential growth rate has to live somewhere in between here. And you can probably even show that it should be strictly in between there. And so what number is it? Right? It's somewhere between two integers. And that was the thing you can think a little bit about it first. We can do some guessing, right? Who thinks it's closer to free groups? Who thinks it? So raise your hand if you think it's closer to free groups. And raise your hand if you think it's closer to that. Okay, and raise your hand if you just want me to get on and stop asking stupid questions. That's okay. I'll have a word with the people who raise their hand afterwards. But okay, so here's the theorem, and it's very surprising. So we take the free inverse monoid of rank R, and we take this just to change variables to make things easier to state. We take P as 2R minus 1. Then the growth rate, which is a number between 2R minus 1 and 2R, is the largest real root of this polynomial. This is typically an irreducible polynomial. So there's no stupid trick we can do here, right? This is some very strange algebraic number. And just to convince you, for r equals 2, the growth rate is 11 over 6 plus the square root of 13 over 2, which is about, I'm sure we can all see that this is between 3 and 4, right? But just to convince you, it's 3.6361. And the people, the eyes have it and say that, well, the ones that on the right, well done. It's closer to, in the limit actually, it means, it's essentially saying you're not identifying it. And I remember when I spoke to another semigroup theorist, my academic grandfather, I mentioned this result to him and I said, oh, in the rank 2 case, we have this thing. I thought it's quite a neat illustration of how strange these numbers are. And he kind of looked at me and said, well done, you can solve quadratic polynomials. And I was kind of, well, it made me a bit less excited, but this is our result. And the proof is, well, the proof is interesting. So it's short enough to fit on a 1 page in the following sense. So we're counting some kind of, in this case, I convince you that there's some sort of counting of paths, right? We'll be counting Mun trees. That's the key idea. So we're counting Mun trees with distinguished vertices, and suddenly we get into some nice combinatorics of counting trees with 2 roots, and there's all sorts of combinatorics you can do. And basically, there's something called Catalan Fuss numbers. Now, sometimes in the literature, these are called Fuss-Catalan numbers, but as another CF, I think I prefer this Catalan Fuss, right? I think this is, so these CF numbers are used to count these trees. And then you start crunching the combinatorics, And it's easy to see that for the even case sphere of radius n, you get this expression, and the odd case, you get this, obviously, right? Now, that's the easy step, in the sense that it's kind of plugging in some horrible binomial coefficients into each other. And then we start to, this is where Richard really came in handy, because he's a sort of master of doing this. You take Stirling's approximation, and you wield it like a weapon, and you close your eyes and just keep hitting it until this polynomial falls out. That's kind of the, I mean, of course, there are a lot more really nice tools, and we even had to take a derivative. And it's like, it's almost not algebra anymore. And eventually this polynomial falls out. And to put it mildly, we don't really know why it's this polynomial, other than that it's irreducible for most values we checked. So we checked all the values up to the root of, up until the rank being 4,000, something like this. So with magma, we just checked, is it irreducible? And it says, yes, it's always irreducible, except when the rank is 5. Well, we don't really know why that happens, but something miraculous happens, and so this strange polynomial just falls out. And we don't know why it happens, but obviously there's some combinatorial tree counting going on. Okay, so I'll expect you all to be able to do this after this talk. I still kind of get nightmares remembering reading through what proofreading this paper was like, because it was sort of, there were always some binomial coefficients that were mistyped, and but of course it won't be very insightful to go through. So instead I'd like to talk a little bit about some other types of algebraic structures and how one can study their growth. And well, in particular, there's when you change the generating set. I mean, this, just to be clear, in the statement of this theorem, I say the exponential growth rate. I'm lying a little bit just to make the theorem look cooler. Because this is the exponential growth rate with respect to the natural generating set. Right? So what happens if I change the generating set? Well, you could do that for free groups too, for example. And there's some recent very, very beautiful work on this. And you can change finite generating set, and you get a whole bunch of different exponential growth rates. Of course, it'll still be exponential, but you'll get some different stuff. And there's some beautiful stuff, this is just from a few years ago now, by Fujiwara and Sella, that if you take any hyperbolic group, the set of growth rates you obtain this way is well ordered. In particular, there's a minimum, and you can really you can talk about the second smallest, and you can talk about all sorts of really beautiful stuff. They compute the order type of it as well. And they even prove that the same holds for any finitely generated sub-semigroup. So that's two more semigroup theorists. I mean, this is really exponential growth rate of the number of semigroup theorists. It's really fantastic. And so if you look at the growth rate of any finitely generated free monoid, it's well ordered. Now, that's not very interesting, because if you take a free monoid, well, there's only really one generating set for that, typically speaking, unless you have something that's redundant. But you can look at sub-semigroups of free monoids, and that becomes very interesting. And you get all sorts of purely semigroup theoretic questions that appear. And of course, there's this very, very natural question, which is, well, what if you take the set of growth rates of free inverse monoids? Is that also well ordered? We don't know. Probably the answer is yes, because usually you can inherit a lot of these properties. But as you saw already, computing the growth of free groups with the natural generating set is more or less trivial. But for free inverse monoids, it's hard. And so suddenly there's an extra layer of difficulty to get through. And there's a very nice result from some time ago by Arjan Silva and Lucenac, which is that if you have a hyperbolic proper quotient of a hyperbolic group, then that will have strictly smaller rates of growth. I kind of alluded to this previously, that when you quotient out by things, you should get smaller growth rates. And that kind of implies some nice Hopfian properties in particular, but also that it leads to a very natural question where you can ask purely geometric questions about these Schützenberger graphs, which I haven't talked very much about. Admittedly, this question only makes sense in that context. But there's some geometric properties of inverse semigroups. And you can ask about whether it's isomorphic to some proper quotient of itself. And that's a purely algebraic question. And suddenly there's geometric semigroup theory all over the place that you can start asking. It's a very natural thing to do. Good. So for the remaining half of the talk, I'll turn to another avenue of this kind of this kind of thing. And the question of computing growth typically will be a very combinatorial question. Now, it has a geometric interpretation, but it's a combinatorial question, and even for groups, there are some really useful combinatorial tools you can use, and they're useful for a lot of other things too. And one of those tools is called rewriting systems. So I'll do a very quick rundown of these. If you've seen them before, it's great. Hopefully, this should be clear enough that even if you haven't, it should be fine. So a rewriting system is just a collection of rules, but we direct them from left to right. So like with a group, the problem about group presentations or any presentation is that we can apply relations either from left to right or right to left. And this is just saying, well, let's get rid of that problem and just go from left to right. And so we have these rules, and we induce kind of rewriting relations where we rewrite things in arbitrarily many steps, finitely many steps. And we also get, essentially, if we forget about the direction and say we can apply either direction, we recover essentially the theory of presentations. So it's kind of a one-sided theory of presentations. And just as a little example that I'll draw probably here. So as an example of a rewriting system is something like AB goes to BA. It's probably the simplest example of a rewriting system. Well, I can apply that to some words like AA, B, AB. And of course, there are many ways of applying my rule to this word. For example, I can spot my AB here and rewrite the word to A, BA, it's terrible chalk. A, BA, BA, B. There. Or I could apply to this and get A, B, 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 A. Whenever I do these things, very nice. Whenever I do these things, because I'm Swedish, I always try and get an ABBA in there. And subconsciously, I managed to do that. So that's just a little national, patriotic pride. Ignore the blue line, it's really not mathematical in any way. And now, of course, I could keep applying these rules in some way, and it's not so hard to see, and I'll get to that property in a second, that no matter how I rewrite it, I'll always get to the point, well, I'm pushing my B's to the left, right? And it's a kind of unique way of doing it. And in this case, well, I have 3 B's, B, and 3 A's, and here I can't apply any more rules, right? And this is an irreducible word, and certainly I'll never be able to have an infinite rewriting, and no matter how I diverge, I'll always flow back to the bottom. I'll mention this property in a second. So certainly this is an example of a terminating rewriting system. I could do something, to get a non-terminating system, I could do something stupid like A goes to A squared, something like that. Of course, I could just keep rewriting that infinitely. I just hit this, oh, there you go, nice. And a rewriting system can be what's called either locally or globally confluent. And confluent, well, if you know your Latin, that means flowing together, right? So this is the confluence property. Local confluence means that whenever I have a small little diamond, so global confluence means that the entire thing flows together, and local means that any single step rewriting can be flowed together. We can flew them together. And that, of course, gives rise to a kind of, if it's terminating, we get some unique normal forms. I won't get into too much how to prove termination or to prove local confluence, because typically those things will be undecidable. Local confluence can be decidable, but confluence in general will be undecidable. So we get into kind of a realm of a very interesting toolkit, but a little bit outside of what I'll be talking about. But there is this nice theorem by Newman, which says that if you have a terminating rewriting system, as long as we know that it always terminates, and we can unify these small little diamonds, which can more or less be checked, or can be checked in this case, then we'll actually get a globally confluent system. So it's like a local to global property, and this is very useful in practice. We get something called a complete rewriting system if we can get unique descendants, and we always get something that becomes irreducible. And if we have some monoid or group or whatever that has where the relations form a complete rewriting system, then we can solve the word problem. I mean, all I have to do is just apply my relations stupidly from left to right, however I want to do it. And then eventually, because it's complete, I'll get something unique. and then I just compare. If I want to compare two words, all I have to do is compare their normal forms. It's like Dan's algorithm is confluent on the words representing 1, right? If I have a word that's equal to 1 in a surface group or anything like that, a hyperbolic group really, all I have to do is just keep finding these forms and then just rewrite it, and if I don't get 1, it's not 1. If I get 1, it's 1. And some examples is this bicyclic monoid, or bicyclic monoid, which I did before. Here it actually suffices to just rewrite from left to right. If I spot a BC, I get rid of it. Otherwise, I don't do anything. Of course, we all know how to do this in free groups, right? There's a confluence property. No matter how I do free reductions, I always get a unique freely reduced word, right? This is something we take for granted, but this is the technology used to prove this fairly simple fact. This AB goes to BA. This obviously defines a kind of something commutative because A and B commute, and it turns out to be, well, the direct product of two natural numbers, the two copies of the natural numbers. But also, just to throw in a little bit of geometry here in non-positive curvature, to wake everyone up again, surface groups, right? So these are, we know we can solve the word problem. Dan told us, a million years ago, but we can actually solve it using these very nice, purely algorithmic, stupid systems. So Hermiller gave a really beautiful example, really beautiful construction for doing this, and it actually reveals a lot of algebraic information too. And that's because there's a connection with this property of being FP infinity, so this homological finiteness properties. So it's not just combinatorial, but there's a beautiful construction by Craig Squire and Yuji Kobayashi, and there's also, one can attribute this in many ways. There's also some very important contributions by Kent Brown and Daniel Groves. But it essentially says, in a simplified form, if I take a monoid, or a group, or whatever, admitting a finite complete rewriting system, then the monoid M is of type FP3. So we saw F3 in the previous talk, but FP3 is just taking, there's some finite projective resolution. There's a projective resolution which is finitely generated in the first 3 dimension of Z. And so this is just the same as for groups. You can do it exactly the same thing for monoids. Right? Nowhere in the homological algebra of groups do we use inverses, and so we can do this verbatim the same way. We can define Tor and X functors and all that fun stuff. But actually, Kobayashi showed that, well, we can even do better. We can do FP infinity. So we can extend this to, there exists a finitely generated, there's a resolution which is finitely generated in every dimension. And actually, it's explicitly computable from this finite complete writing system. It effectively consists of looking at how words overlap. And so this gives a lot of homological information. In particular, it says that all the cohomology groups are finitely generated and computable explicitly. So if you have a group that emits a finite complete writing system, you can compute all of the cohomology. Yes?
So admitting means for what problem?
Right, so that's a good point. So admitting here, I mean, there exists some finite presentation for the monoid, or group, or whatever, such that the relations are a complete rewriting system. So when you look from left to right, it's a complete system. However, it could be over some different generating set. And in fact, this property of being admitting a finite complete writing system, in general, of course, is a property of monoids or groups. But if you fix the alphabet, then it might be that even though if you change the alphabet, you can admit some finite complete writing system, but you can't do it over that alphabet. It's too small. So it's a bit of a subtle property, but in general it just means there exists some complete presentation which is isomorphic, which defines something isomorphic too. And one of the really nice consequences of this is this old construction when you combine it with something that Stallings did, which is that there's a group which is not FP3, but which still has decidable word problem. Right? So this is the stuff that was extended by Bisfine and Brady, and Squire, who was a student of Stallings, I believe, combined this with his own result to get this. So there's a finitely presented group G, where you can solve the word problem, but you cannot find the complete rewriting system for it, a finite complete rewriting system. So this is sort of a niceness property that's even stronger than having decidable word. And one of the things that makes it very, very nice is computing growth. So, and to illustrate that, well, certainly, I'm not going to expect you to remember the very first thing I said during the talk, But that was that a monoid is regular if we have this pseudo-inverse. So it's like an inverse monoid, but it's not necessarily unique. And it turns out that even though I said that free inverse monoids exist, there's a theorem by McAllister which says that free regular monoids, whatever that would be, don't exist. And the problem is, I told you that there's this HSP theorem. The problem here is that there's no S. Subobjects are not necessarily preserved, because when we have a regular monoid, unlike in the case of inverse monoids, where I can just, or in groups, in a group I can always, if I want to know what the inverse of an element is, I can just write inverse. I can add an inverse symbol, and there you go, that's the inverse. It's a distinguished inverse. But in this, because there's no uniqueness, there's no distinguished sort of pseudo-inverse to choose from. There could be lots of them. And in fact, usually there will be lots of them, otherwise it's going to be an inverse monoid. And so there's no distinguished pseudo-inverse, and one might want to kind of wonder what happens what if I force there to be a unique pseudo-inverse? And there's this article by James East, Bob Gray, Asif Mohammed, and Nick Rushkut, which appeared quite recently. And it's this presentation, it's a monoid, where you just take these relations that make it look, you just say that for every word, I have some star word, something that behaves like an inverse, and I just force that to be the inverse. I say I'm allowing a little star symbol that behaves like inverses, and it's really distinguishing some pseudo-inverse. And these are called free regular star monoids, and it turns out that they genuinely are free. They're not typically finitely presented. You'll notice that I'm looking at all words here over my alphabet. And in general, you can't get rid of that. You need all those infinitely many relations. And actually, using these rewriting systems, which I'll get to in a second again, you can show that, this is something I did recently, is that these free regular star monoids are not even FP2. Now, free things should be nice, homologically speaking, you might think, but this is an example of where this is really failing. And actually, the second homology group, the second integral homology group, is even, well, it's infinite, it's Z infinity. Well, certainly it's going to be infinite, but it's not finitely generated. And this is one of the ways you can interpret that is a purely algebraic way of saying that all of these relations are strictly independent of each other, more or less. There's really no redundancy going on other than some obvious things. This is in Martin's the very first talk, right? There were some connections between deficiencies of groups and essentially that there's some homological things you can do to try and understand whether you have redundant generators or redundant relations. And this is basically in the opposite end of the spectrum where it's saying that there's such a strong homological characterization saying that nothing's redundant. Okay, so, well, one of the questions I decided to ask myself after doing this growth of free inverse monoids was, well, how fast do these guys grow? And I was very, very surprised at what it turned out to be. And in the rank 1 case, so this is the monogenic case, right? We have one generator, it should be Z. But of course, that's one generator together with a star. So really, I have two generators A and B. So A and A star, really, but I'll call them A and B. And they satisfy these relations for all I. So it's just some nice rewriting system. And this turns out to be complete. You can show that. It's fairly tricky to show, but it turns out to be a complete system. And so we can now use that to compute the growth and homology. And so in particular, the ball of radius n in this whatever this algebraic object is, ooh, that's a slightly different typeset, but those are the same. The ball of radius n is just, well, all the set of irreducible words. So the words that don't have any left-hand side from these rules. Now change to zeros and ones because there'll be a connection with some other binary words. But really, that's now an explicit formula, or an implicit formula, if you will, really, for saying how fast these guys should grow. And in a very different, and you might wonder how you count that. And I'm going to leave that problem for a second. I'm going to call it x sub n. And so the growth of these balls is just going to be the size of x sub n. And in a very different context, some people studied, well, they just take this purely combinatorial problem. So how many binary strings of length less than or equal to n are there, which avoids these kind of palindrome style things. So we should avoid things like 0, 0, 1, this is W, 1, 0, 0, 0, 0, 1. So for various reasons that I can't get into, looking at the binary strings which do not contain sub-patterns of this form. So this is one of the examples of patterns that, in a binary string that you would not allow. That has some interesting applications in theoretical computer science, and so they decided to count them. They asked, how many are there? I'm gonna, just in the interest of stating a theorem in a slightly slicker way, I'm gonna introduce a kind of filtration on these, just saying that, well, I take, instead of saying x sub n, I'll say x sub n, the kth iteration of that, where I take the same definition, but I only allow those up, I'm only disallowing those up to size k. So I'm only forbidding finitely many words. Okay? So I'm disallowing those patterns up to length k, and then after that I don't really care if I'm omitting them or not. And I do the same thing here, so the same is just saying the binary strings of length at most n, avoiding w for all words of length at most k. Okay, this is disallowing a finite set, so this is a regular language. There's a finite automaton for describing it. And Curry and Rampersad proved that this, strangely, this y sub n has intermediate growth. And actually, it turns out that these are exactly the same, they grow exactly the same size. They're not the same sets, but they have exactly the same size. There's a very nice bijection between them. And so in particular, this monogenic, monogenic should be like Z, but there's a monogenic algebraic object which has intermediate growth. And that's very strange to me. I found that very, very surprising. There's a nice little alternative way using something called the Golden-Jackson cluster method that one can use to show this, but it's quite messy, and I won't really get into that. And just for my final slide, I kind of like torturing myself by looking at these numbers, how they prove that it's intermediate. And the way, well, the way they do it is that they find a bijection between these binary strings of length n, avoiding these patterns, and something called strongly unimodal sequences. And they're actually quite a nice combinatorial definition. It's sort of like a partition. So if I just had the second condition, I'm basically just describing a partition as long as it's decreasing in size. But here I'm saying that it increases until some point and then it decreases. So that's it's kind of like a partition-like combinatorial object. This is, you might as well see this in an undergraduate combinatorics class. And the weird thing is that, well, the number of strongly unimodal sequences of length n, where n is the whatever number they sum to, well, it grows like this function un, and it's known via something called Ramanujan Mach theta functions. And I was very happy to use the name Ramanujan in an article on like semigroup theory. And they proved that it grows like this weird function, plus a bit of a correction, where these beta sub r are explicitly computable. For example, beta 1 is 2 pi squared plus 9 over 64 pi squared root of 24. And then Curry and Rampersad proved that you can actually sandwich this y sub n between this y tilde, which is obtained from yn in a non-trivial way, to get this horrible thing. Like, this is what I thought maths would look like when I was like in high school or something. Like, surely this is what research maths look like. There's pi everywhere and square roots and weird e to the pi, whatever, right? This looks AI generated, at least, right? But this is, and of course none of this is my work in that sense, right? This is some very hardcore number theory, but I find it very nice to have the connection. And obviously this has intermediate growth. And obviously is taken with a very big pinch of salt, because if someone told me this grows exponentially, there's an exp there, right? Then I believe them, but it turns out that it's intermediate. Anyway, for higher ranks, I still don't know what the growth rate should be, and I suspect it will even be more complicated. It's going to be exponential, but if this is what happens in the rank 1 case, I'd prefer if someone else did the higher ranks. Thank you.
There's time for 1 or 2 quick questions.
Yeah.
On the top of slide 14, why this is a writing system for F1 star?
Yeah, so that's a good question. So first of all, let's agree that we can almost agree that it defines it. Whether it's a complete system or not is a different question. But what relation should we have? Well, we should have that W star W should be equal to W, for example. Now I have all the words, my alphabet will be A and B, so A and A star. And so I'll at least have the rules of the form A to the I, B to the I, A to the I equals A to the I. Now you might object and say, surely I should have something like AB, BA, AB is AB as well. But it turns out that if you look at this now, then no, AB, sorry, not AB, BA, AB, AB, AB. Because this is just saying A star, and if you do A star, star, that's the same thing as A star, right? Because I'm applying, it's like if I apply, what do? I apply the stars and I change the order, just like for inverses. And here, I see an ABA, right? There's an ABA in here, and so that will be rewritten by the previous rule. And so it turns out that these plus the opposite is sufficient, but it's not obvious. There's a little bit of trickery going on that I've hidden. But it turns out that it's sufficient. It's a very reasonable question.
In the interest of time, I think we should keep the questions for after the next talk so that we can have a short break before the next one. So let's thank Carl-Fredrik again.
Thank you.